History itself rests on an illusion of knowledge. We think we understand the path of human progress, but the true story of our first inventors has been buried for thousands of years. This journey into the forgotten inventions of prehistory will completely reshape your understanding of human ingenuity. We will unearth the lost machines that built our world, from revolutionary hunting tools to the first applications of physics. How did ancient engineers move mountains of stone without wheels? And why were their most brilliant creations ultimately erased from memory? What does it truly mean to be the first builder of a machine? A small community huddles not just for warmth, but around a crackling fire that serves as their first laboratory. This was the world of the Paleolithic and Neolithic eras, a stage set for a quiet revolution. Our ancestors were not merely surviving, they were responding to immense pressures, from shifting climates that altered landscapes to the constant need for more efficient ways to hunt and gather food. These challenges became the ultimate catalyst, pushing human thought toward a new horizon. It was here that the foundational principles of machine building were first discovered. The leap required was not just physical, but profoundly cognitive. As archaeologist Stephen Mithen explores in his work The Prehistory of the Mind, our ancestors had to move beyond simply using a found rock or stick. They began to envision a tool that did not exist, to plan its shape, and to execute its creation for a specific purpose. This was the birth of applied physics in its most elemental form. It was an intuitive grasp of leverage, the force needed to chip one stone with another. It was an understanding of tension, how a sinew string could store energy. It was a recognition of motion, how a shaped edge could make a task easier. So what does it mean to be the first builder? It is to look at the raw, unformed world and see hidden potential. It is to solve a problem not with muscle alone, but with a concept made real. Their worldview was one of direct interaction with materials, where every action had a tangible, immediate consequence. This foundational shift in human cognition, from using to creating, set the stage for everything that would follow. It prepared the ground for the tangible and often startling evidence these first engineers left behind for us to find. The genius of the first machines lies hidden within their elegant simplicity. Think of a seed, a tiny vessel that holds within it the complete blueprint for a towering oak tree. In the same way, a simple prehistoric tool, like a sharpened stone or a wooden lever, contains the entire conceptual DNA for the complex machinery that would follow. To see this, we must strip away our modern expectations of engines and electronics and return to a fundamental truth. A machine, in its purest form, is any device that redirects or amplifies a force to make a task easier. It grants its user a mechanical advantage, a way to achieve more with less effort. This is the core principle that engineers like Henry Petroski point to when they identify the lever as the quintessential machine. Its beauty is in its sheer simplicity. Consider a hunter-gatherer using a long, sturdy stick to pry a heavy root from the earth. That person is not just foraging. They are applying the law of the lever. They are placing a fulcrum, applying force at one end, and watching as a much greater force lifts the root at the other. In that single, purposeful action, physics is harnessed. Human intention is made manifest in the material world. This reframing is not just academic. It is a key that unlocks a new way of seeing the past. Suddenly, the polished hand axe is not merely a cutting tool. It is a device that concentrates the force of a swing into a fine, durable edge. A weighted digging stick becomes a percussive machine, transferring energy from the user's arms into the compacted soil. By broadening our definition of what a machine can be, we begin to perceive the profound sophistication in objects we might have dismissed as ordinary. We start our search not for gears and pulleys, but for the foundational ideas that made them possible. And with this new lens, we can now journey to a specific place and time where one of these first machines forever changed the relationship between humans and their world. A carefully carved piece of wood, shaped by hand and tested through generations, became one of our first extensions into the world of physics. This was the throwing stick, a device so elegantly simple that its true genius is often overlooked. It was not a mere club swung with brute force. It was a machine designed for flight. A hunter would hold this curved wood, feeling its balance, and with a precise flick of the wrist, transfer the energy of their body into a spinning, soaring projectile. This action required an intuitive understanding of principles we now call aerodynamics and rotational force. The stick was engineered to travel farther and hit harder than any rock thrown by hand, effectively extending the hunter's reach and transforming the very nature of the hunt. This was not a solitary invention. Cultures across the globe independently arrived at this same brilliant concept. The returning boomerangs of indigenous Australian peoples are the most famous examples, marvels of design that curve back to the thrower. But non-returning throwing sticks, often called rabbit sticks, were used with devastating effectiveness by ancient peoples in North America. They have even been found placed with great care in the tombs of Egyptian nobility, signaling their immense value. Each of these artifacts represents a profound cognitive leap. The creator had to visualize the entire flight path before the stick ever left their hand. They had to calculate the needed force, the optimal angle of release, and the precise spin required for a stable trajectory. This was applied physics in its most direct and consequential form. The process of creating these tools was humanity's first research and development department. A craftsperson would select a specific type of wood, shape it over time, test its flight, and then subtly adjust the design based on the results. A bend that was too sharp might cause it to dive into the ground. A section that was too heavy on one end would make it tumble unpredictably. Through this cycle of trial, observation, and refinement, knowledge was accumulated and passed down. The principles of leverage and force transfer learned from the lever were now applied to motion through the air. This foundational knowledge of projectiles, hard-won through the crafting of wood, would eventually pave the way for the next great leap in hunting technology. It set the stage for a machine so powerful it could bring down creatures many times the size of a human. That same understanding of force and motion, first tested with a spinning stick, would soon be pushed to its absolute limits. A new kind of machine was needed to confront a new kind of challenge, one that waited in the frigid Arctic waters. Picture a hunter standing on an icy shore, facing a creature of immense size and power, a seal or even a whale. A simple spear would be useless. It might wound the animal, but it would pull free almost immediately, leaving the hunter with nothing and the animal to suffer. The problem was not just piercing the hide, but securing the catch. The solution was an invention of breathtaking cleverness, the toggle harpoon. This was not a single tool, but a sophisticated system of interconnected parts, a true assembly. Its point was a carefully carved head made of bone or ivory, designed to be sharp enough to penetrate thick blubber, but the true genius was in its mechanism. This head was not fixed to the main shaft. Instead, it was attached with a length of strong sinew, and it was shaped with a subtle pivot. When the hunter thrust the harpoon forward, the head would strike and embed itself. Then, as the animal struggled, the tension on the sinew line would cause the head to rotate, or toggle, 90 degrees sideways inside the wound. This simple pivot created an anchor, a lock that made the harpoon head almost impossible to pull out. It was a machine engineered for a single, devastating purpose: to convert the prey's own escape attempts into a more secure hold. This device required an intimate knowledge of materials. The bone head had to be hard enough to hold an edge. The sinew cord had to be strong enough to withstand immense pulling force without snapping. The wooden shaft had to be both light enough to throw and sturdy enough not to splinter. Each component was selected and fashioned for its specific role in a coordinated mechanical sequence. The success of this technology was not just a matter of a single meal. It was the key to survival in one of the most demanding environments on Earth. The toggle harpoon allowed cultures to reliably hunt the massive marine mammals that were central to their way of life, providing not just food, but also oil for light and heat, and bones for building materials. This single, brilliant machine made the long-term settlement of the Arctic possible. It stands as a powerful testament to human ingenuity, proving that our ancestors were not just tool users, but systems thinkers, solving complex problems with elegant mechanical solutions. And as these early builders mastered the art of survival, their ambitions grew, leading them to attempt projects of a scale that seems almost impossible to believe. Deep within the cave, another kind of machine was at work, one that operated not with force but with patient control. An artisan would heat a heavy, grooved stone near a fire, then slowly and methodically draw a wooden spear shaft back and forth through the lubricated groove. This was the shaft straightener, a device dedicated not to creating a tool but to perfecting it. The goal was absolute straightness, a quality essential for any projectile meant to fly true. This seemingly simple act was a sophisticated application of early physics. The heat made the wood fibers more pliable, while the constant, guided pressure from the groove coerced any warps or bends into submission. It was a direct manipulation of material properties, an early form of thermodynamics in practice. Discoveries of these grooved stones at sites across Europe and North America reveal a universal truth recognized by separate cultures. A bent spear was not just an imperfect tool, it was a dangerous liability. It could veer off target, wasting a precious hunting opportunity, or worse, fail to penetrate deeply enough, allowing a wounded animal to escape. The shaft straightener was, in essence, the world's first quality control machine. It ensured consistency and reliability, turning a roughly hewn stick into a precision instrument. The very existence of such a specialized tool speaks volumes about the society that created it. It suggests that certain individuals had the time and skill to dedicate themselves to this meticulous craft, hinting at an early division of labor. It also shows that these communities placed a high value on perfection, understanding that the success of the hunt, and therefore their survival, depended on the flawless performance of their technology. This relentless pursuit of precision, embedded in a simple grooved stone, points toward the complex cultural systems that were beginning to form around these brilliant inventions. That rhythmic sound, stone grinding against stone for hours on end, was the pulse of a new age. This was not the quick, sharp chipping of flint, but a slow, deliberate process of creation. The emergence of the Groundstone axe, painstakingly shaped from incredibly hard materials like nephrite, represented a fundamental change in humanity's relationship with the physical world. A simple, chipped flint tool was effective for cutting and scraping, but it was brittle and would dull quickly against hard wood. The new polished axe was something else entirely, a machine built for relentless, repeated impact. Its creation was a feat of both patience and profound geological knowledge. The maker had to first locate a specific type of tough, non-porous stone, often traveling great distances to find the right material. Then, using a coarse grinding slab and abrasive sand mixed with water, they would slowly wear the rock into its general shape. The final stage, the polishing, could take days of meticulous work, using finer and finer abrasives to create a surface that was not just sharp, but incredibly strong and smooth. This was an immense investment of labor, a commitment to creating a tool that would last for generations. The result was a device of transformative power. With a polished stone axe head securely hafted to a strong wooden handle, a single individual could do what was previously the work of many. They could fell large trees, clearing land for the first time in human history. They could shape timber for building permanent structures, for crafting sledges and early boats. This tool did not just help people adapt to their environment, it gave them the power to reshape it. The landscape itself began to change under the steady, repeated swing of the polished axe. This new machine was so vital that it became more than just a tool. It became a symbol of status and identity. A beautifully polished nephrite axe passing from a parent to a child was a tangible link to the past and a promise for the future. It represented knowledge, skill, and the authority that comes from being able to build and provide. The axe cleared the literal ground for agriculture and settled life, but it also cleared a conceptual space for new kinds of society to take root. With the power to reshape their world now firmly in hand, these early builders turned their attention to an even greater challenge, one that required moving the earth itself. The steady rhythm of the axe clearing land created a world with new needs, a world that required not just strength but perfect symmetry. A quiet revolution was spinning to life in the hands of Mesopotamian artisans. Before this moment, every clay pot was built by hand, its form a testament to patient coiling and pinching, often resulting in thick, uneven walls. The introduction of the potter's wheel changed everything. This was not merely a new tool, it was a true machine, a dynamic system that harnessed an invisible physical force. At its heart were two simple components: a heavy stone flywheel at the bottom and a spinning platform or spindle on top. The potter would set the massive wheel in motion with their foot, a coordinated dance of hand and limb that required immense skill. As the clay spun, it was subjected to centrifugal force, that same push you feel on a merry-go-round, which naturally pulled the material outward into a beautifully symmetrical shape. This force allowed the artisan to use their fingers not to build the walls, but to guide them, drawing the clay upward into thin, uniform vessels with a speed and consistency that was previously unimaginable. The impact of this machine rippled far beyond the workshop. It democratized the production of essential goods. What was once a labor-intensive craft became more efficient, leading to an abundance of storage jars for grain and oil, sturdy cookware for daily meals, and finally made ritual objects for cultural practices. This abundance in turn stabilized food supplies and fueled trade networks, as these standardized, high-quality pots became valuable commodities in their own right. The true legacy of the potter's wheel, however, lies in the principles it embedded in human thought. The potter had to master rotational inertia, understanding how the heavy flywheel stored energy to maintain a smooth spin. They worked with angular momentum, learning to control the speed to prevent the soft clay from collapsing. These are the very same laws of physics that govern the massive turbines in power plants and the engines in modern vehicles. With this machine, humanity learned to control sustained rotation, a foundational concept that would one day drive the gears of entire civilizations. This mastery over spin and force paved the way for an even more ambitious application of rotation, one that would confront the greatest logistical challenge of the ancient world. That same mastery of spin which shaped clay on the wheel was harnessed for a far more elemental purpose, the creation of fire itself. The bow drill stands as one of history's most elegant machines, a device that turned human effort into a spark of life. Picture a skilled individual kneeling, not with sticks to rub together, but with a compact assembly of wood and cord. They move a bow back and forth, its string looped around a vertical spindle. This spindle spins rapidly, its sharpened tip grinding into a notch on a wooden hearthboard below. Friction builds, wood dust collects, and a thin wisp of smoke begins to curl upward, carrying the scent of charring timber. Then a tiny, glowing ember appears, ready to be gently nurtured into flame. This was not just a new way to make fire, it was liberation. For countless generations, communities were tethered to the embers of a lightning strike or a forest blaze, a constant vigil to keep the hearth alive. The bow drill changed that reality entirely. It placed the power of creation directly into human hands, granting true independence from the whims of nature. This machine was a system of 4 simple, perfectly integrated components. The hearthboard was the foundation, a flat piece of dry, soft wood. The spindle was the engine, a straight, smooth rod of harder wood that transferred the rotational force. The handhold, often a stone or another piece of wood with a depression, stabilized the top of the spindle, allowing it to spin freely under pressure. And the bow, with its taut string wrapped once around the spindle, converted the user's simple back and forth motion into the rapid, continuous rotation that was essential for generating enough heat. This elegant conversion of reciprocal motion into rotary motion is a cornerstone of mechanics, a principle that would later power the steam engines of the industrial age. But its first application was profoundly intimate, the summoning of warmth and light from mere friction. The brilliance of the bow drill extended far beyond the hearth. The same tool with a different drill bit became a master craftsman's essential instrument. It could bore clean, precise holes through tough materials like bone, shell, and hardwoods. This capability unlocked new levels of complexity in tool making, allowing for the assembly of hafted axes with secure wooden handles, or the creation of intricate jewelry and adornments that were sewn onto clothing. It enabled the lashing together of sledges and the construction of more sophisticated shelters. The bow drill was, in effect, the first portable power tool, a single invention that served both the most fundamental human need and the highest aspirations of craft and culture. It represents a pinnacle of prehistoric engineering, where a deep understanding of physics was applied to conquer one of humanity's oldest challenges, and in doing so, opened the door to a new world of making. The plow began as a forked branch, a simple hook dragged through the earth by human hands. This humble act, the first deliberate cut of a furrow, contained the seed of an agricultural revolution. That basic branch slowly evolved into the ard or scratch plow, a true machine designed to leverage strength into landscape transformation. It was a system of 3 key parts: a sturdy draft pole that channeled the pull, a share that cut into the soil, and handles for the farmer to guide its path. At first, human muscle provided the power, a grueling effort that yielded only shallow scratches in the ground. The true leap came when our ancestors made a profound connection, learning to harness the immense, steady power of oxen. This was the moment the machine found its engine, shifting humanity's relationship with energy itself from something generated by our own bodies to a force we could command from the animal world. The rhythmic pace of the ox, coupled with the plow's enduring frame, allowed for the systematic tilling of vast fields. What was once a scattered practice of gardening became a methodical process of farming. This new efficiency did more than just plant seeds. It planted the very idea of surplus. For the first time, a community could reliably produce more food than it needed for immediate survival. That extra grain, stored in great pottery jars made possible by the potter's wheel, became the foundation for everything that followed. It allowed populations to grow and gather in permanent settlements, freeing some individuals from the daily burden of finding food to become artisans, leaders, and priests. The plow, therefore, did not just reshape the soil, it fundamentally tilled the fabric of human society. Its use required new forms of cooperation and, inevitably, new forms of hierarchy. Managing a team of oxen was a major undertaking, demanding shared resources and coordinated labor. The distribution of the best, most fertile land created social distinctions that had not existed in more mobile hunter-gatherer bands. Ownership of a plow and the animals to pull it became a primary source of wealth and influence, structuring communities around land and its management. This machine, born from a forked branch, quietly built the social and economic bedrock upon which cities and empires would eventually rise. Its enduring legacy is the world of settled life we know today, a world shaped not by the spear but by the steady, earth-turning pull of the plow. That iconic symbol of progress, the wheel, hides a deeper secret. Its true power was unlocked not by the disc of wood itself, but by its silent partner, the fixed axle. This pairing represents the eighth forgotten invention, a cognitive leap of staggering proportions. For generations, we picture our ancestors watching a log roll and having a sudden flash of inspiration. The reality was far more complex. The brilliant innovation was not merely understanding that round things roll, but figuring out how to firmly attach a rotating object to a stationary one, creating a stable platform capable of bearing a heavy load. This was the birth of the wheel and axle as a true simple machine. The earliest known wheels, discovered in places like Mesopotamia around 3500 BCE, were not on carts. They were potter's wheels, heavy stone discs that spun on a fixed central pivot. Later, ceremonial wagons used wheels for ritual processions, moving objects of spiritual significance rather than goods for trade. Practical challenge was immense. How do you make a wheel spin freely without wobbling or seizing up? The solution lay in the interface, the precise point where the rotating wheel hub met the non-moving axle. Early engineers discovered that by using lubricants like animal fat or beeswax, they could drastically reduce the friction that would otherwise grind the assembly to a halt. This was applied physics on a grand scale, the management of force and resistance to facilitate smooth, controlled movement. The cognitive shift required to move from a rolling log to a fixed, rotating assembly cannot be overstated. It meant thinking in terms of systems and relationships between parts. The wheel and axle became the purest expression of a simple machine, a device that redirects force to make work easier. With a cart, a person or animal could pull a load many times heavier than they could carry, because the wheel and axle combination effectively conquered friction. This fundamental pairing, perfected in the ancient world, became the literal heart of nearly all mechanical transportation and industry that would follow. From the chariots of empires to the water wheels that powered early factories, the principle remained the same. The forgotten genius was not in inventing the circle, but in taming its spin. Those multi-ton stones, standing silent for millennia, hold within them a silent question. How did human hands, without wheels or metal, move mountains of rock across the land? The answer was not a single tool, but a system, the ninth forgotten invention, the sledge. This was the heavy-duty truck of prehistory, a simple platform of timber mounted on curved runners designed to glide. But its true genius was not in the sledge itself, but in the pathway it traveled. Teams of workers would lay down a track of logs in front of the massive load, creating a temporary road. As the sledge was pulled forward, others would rush to take the logs from the back and place them at the front in a continuous, rolling conveyor belt of wood. To reduce friction even further, they would lubricate this wooden track with water or with animal fat, turning a near-impossible drag into a manageable, albeit grueling, pull. This entire process was a live demonstration of applied physics, a masterful manipulation of weight distribution and the reduction of resistive force. Experimental archaeology has brought these methods back to life with stunning results. In one famous project in Japan, teams successfully moved massive multi-ton stones using nothing but a wooden sledge, ropes, and a crew of dedicated volunteers pulling in unison. The effort required was immense, but it proved conclusively that the technology available in prehistory was more than equal to the task. The rhythmic chanting and coordinated heaving of the teams reveals the other essential component: sophisticated social organization. Moving a single megalith was not a casual effort. It was a monumental logistical undertaking that required a clear chain of command, shared purpose, and the ability to feed and house a large, temporary workforce. The sledge, therefore, was more than a machine. It was a social catalyst. Its use implies a society with the foresight to plan projects that would take generations to complete, and the authority to mobilize entire communities toward a single, awe-inspiring goal. This simple wooden platform challenges our deepest assumptions about prehistory, revealing a world not of isolated struggle, but of coordinated ambition on a breathtaking scale. Along riverbanks and tidal flats, a different kind of machine lay in wait, one built not of moving parts but of patient observation. The fish weir was a labyrinth of wooden stakes and woven nets, a stationary structure that became dynamic through its interaction with the water. This was not a tool wielded by hand, but a system designed to let the river do the work. Its genius was in its passivity, a machine that harvested while its creators slept. The design was elegantly simple, yet it revealed a profound understanding of both hydrology and animal instinct. Long V-shaped fences were constructed to guide the natural flow of migrating fish, funneling them steadily into progressively smaller enclosures until they reached a central holding pen. The current itself became the engine of the harvest, a force carefully channeled and exploited. The scale of some of these constructions is staggering, with remains of ancient weirs stretching for hundreds of feet, still visible at low tide in places like Maine and Wales. These were not the projects of a single family, but of an entire community working in concert, investing immense labor in a structure meant to provide for generations. This required not just cooperation, but foresight, a long-term vision that understood the value of a reliable, renewable food source. The weir was a testament to sustainable thinking, a machine that worked in harmony with the rhythms of nature rather than seeking to dominate them. By selectively harvesting only what was needed and allowing the rest of the population to pass and spawn, these early engineers practiced a form of resource management that ensured the machine's productivity for centuries. The principles embedded in the fish weir, the art of guiding flow and creating purposeful channels, became the conceptual foundation for humanity's later mastery over water. This early hydraulic engineering would eventually be scaled up into the irrigation canals that fed the first farms and the complex water systems that powered entire cities. The quiet intelligence of the weir demonstrates that the first builders were not just shaping stone and wood, but were learning to read the landscape itself, turning the flow of a river into a dependable partner in survival. That rhythmic clacking is the sound of threads being transformed, of individual strands uniting into something far stronger than themselves. The loom stands as the 11th forgotten invention, a machine that did more than produce cloth. It wove the very fabric of society itself. Picture the earliest form, the warp-weighted loom, a tall, upright frame from which hundreds of vertical threads, the warp, hung taut, pulled straight by carefully chosen stones. The weaver's dance was one of intricate coordination, passing a horizontal thread, the weft, through the shed, the space created between alternating warp threads. A wooden sword would then beat the new thread firmly into place, building the textile row by meticulous row. This was not merely craft, it was a form of early automation, a machine that managed the relentless repetition of the over-under pattern, freeing the human hand to focus on complexity and design. This systematic process required a precise, almost mathematical understanding of geometry and pattern creation. The weaver had to hold a mental blueprint of the final textile, counting threads and sequences to create stripes, checks, and eventually, the elaborate symbols that told stories of lineage and belief. The machine enabled a scale of production previously unimaginable. From these looms came the sturdy woolen sails that caught the wind, powering the boats that would connect continents. They produced the dense, layered textiles that served as early armor, protecting warriors and turning the tide of conflicts. But the true impact of the loom resonated within the community. Weaving was a time-intensive process, one that naturally drew people together. It became a profoundly social activity, a space where knowledge, stories, and songs were shared and passed down through generations as hands moved in practiced rhythm. This machine, therefore, did not just create material, it fostered communication and cemented cultural identity. The loom literally and figuratively wove society together, binding individuals into a cohesive whole with every thread crossed and beaten into place. A simple woven mat catching a gust of wind transformed a drifting raft into a living machine. This was the sail, the moment humanity learned to build an engine that required no fuel, only understanding. Before the first wooden hull was carved, our ancestors were lashing together logs and raising primitive sails to harness the invisible power of the air. The evidence for this audacious early seafaring is written across the deep past. The initial peopling of Australia, an event that occurred more than 50,000 years ago, stands as a silent testament to their capabilities. Reaching that continent required crossing open water, a formidable stretch of ocean that separates it from Southeast Asia even at the lowest sea levels. This was not an accidental drift but a deliberate voyage, likely undertaken on some form of basic watercraft equipped with a sail. This single act represents one of the most profound cognitive leaps in human history. The builders of these first vessels had to grasp a new kind of physics, the principles of aerodynamics that allow a curved surface to pull an object forward. They were no longer just redirecting force with a lever or storing it in a bow. They were capturing the wild, unpredictable wind itself and bending it to their will. This machine did more than move people across water, it moved entire cultures. A sailing raft became a vehicle for goods, for new technologies, and for ideas, connecting distant shores and catalyzing an exchange that would shape the trajectory of human societies. Mastering this machine meant learning to read the world on a grand scale. Early mariners had to become intimate with the seasonal patterns of the winds, the hidden rivers of ocean currents, and the silent, guiding map of the stars at night. They were not just sailors, they were holistic engineers, integrating knowledge from meteorology, astronomy, and hydrodynamics into a single, practical system for survival and exploration. The sail asked its users to see the environment not as a series of obstacles, but as a complex, interconnected set of forces to be navigated and understood. This shift in perspective from battling nature to working with its rhythms was perhaps its greatest legacy. With the wind now a willing partner, the horizons of the human world expanded beyond the coastline, reaching for lands waiting beyond the curve of the sea. That mastery of fire, once summoned with a bow drill, now demanded a new kind of home. The enclosed oven became a vault for thermal energy, a machine that transformed raw heat into a tool of immense precision. This was not an open flame for roasting, but a contained chamber where temperatures could be managed and sustained for hours. The earliest versions were simple pits dug into the earth and lined with hot stones, but the true leap came with the clay dome, an architectural structure designed to trap and circulate heat with remarkable efficiency. Inside this sealed space, heat was no longer a fleeting element to be fought against. It was a resource to be carefully controlled. This shift from direct to indirect heating unlocked possibilities that reshaped human health and technology. One of its most profound impacts was on the very food our ancestors ate. Many wild plants, like certain tubers and grains, contain natural compounds that are difficult for the human body to process. The consistent, enveloping heat of an oven acted like a slow, thorough purification system. It broke down these tough fibers and neutralized mild toxins, making a wider variety of plants safe and nutritious to consume. Hard, dry grains could be transformed into easily digestible porridges and, eventually, into the very first loaves of bread. This thermal processing effectively expanded the menu of prehistory, turning previously marginal food sources into dietary staples that could support larger, healthier populations. The same principles of controlled heat that baked bread were soon applied to the world of materials. A simple clay pot dried by a fire was fragile, but one fired inside the steady heat of an oven underwent a chemical transformation. The minerals within the clay fused together in a process called sintering, creating a vessel that was waterproof, durable, and able to withstand daily use for generations. This was the birth of true ceramics, a technology that revolutionized storage and cooking. The oven was a versatile thermal engine, its purpose defined by the temperature it achieved. A lower, steady heat perfected pottery. A more intense, focused heat, carefully managed with airflow, could then be turned toward rocks. Certain stones, when subjected to this blistering environment, would release their metallic content in a liquid stream, a process we know as smelting. The first copper and tin were likely discovered by accident when ore-rich rocks were used to line a fire pit, but it was the controlled atmosphere of the oven that made this process repeatable and intentional. This multi-purpose machine, therefore, sits at the very foundation of multiple revolutions. It improved nutrition through baking, created enduring goods through ceramic firing, and ultimately unlocked the secrets of metal itself. The oven's legacy is the understanding that heat is not merely warmth, but a precise force that can transmute the very nature of matter, setting the stage for every furnace and forge that would follow. A simple pole with a bucket and a stone could lift an entire civilization. Along the life-giving rivers like the Nile, the challenge was not a lack of water, but a matter of distance. The river's bounty was confined to its immediate banks, while the sun-baked lands just a short walk away remained barren. The solution was a machine of elegant balance, the Shaduf. This was the lever, humanity's oldest mechanical ally, put to work in its most vital role. A long pole was mounted on an upright frame, with a leather bucket hanging from one end and a heavy counterweight of mud or stone fixed to the other. A farmer would pull the bucket down into the river, and the counterweight would make lifting the full container nearly effortless. With a smooth, swinging motion, the water was pivoted up and poured into a waiting ditch, beginning its journey to thirsty crops. This single device turned the back-breaking labor of hauling water into a manageable, rhythmic task. Its true power lay in what it enabled. For the first time, families could establish small farms and gardens on the higher ground away from the crowded, flood-prone riverbanks. This was a quiet revolution in settlement, a dispersal of the population across a wider area. It also allowed for agricultural diversification. as farmers could now reliably water a wider variety of crops beyond the staples that clung to the river's edge, including vegetables and fruit trees that required consistent moisture. This new efficiency created a ripple effect through society, with the Shaduf freeing up countless hours of labor previously devoted to hauling water. That human effort could be redirected. Some individuals could now dedicate themselves fully to perfecting a craft, whether it was weaving finer textiles, shaping more sophisticated pottery, or working the first soft metals. The Shaduf, therefore, did more than water plants. It helped water the seeds of specialized professions. This machine represents a pivotal shift in the human mindset, from simply living with a landscape to actively re-engineering its most fundamental resource, water. The simple act of lifting water with a counterweight was the first, crucial step in a chain of hydraulic engineering that would lead to the vast, state-managed canal systems of Mesopotamia and Egypt. It was a declaration that humanity would no longer be passive recipients of a river's gift, but active partners in shaping its flow. The silent genius of these first machines is woven into the very fibers of the materials themselves. Our ancestors were intuitive material scientists, their workshops the forest, the riverbank, and the quarry. They understood that a dense, fine-grained wood like oak offered the unyielding strength needed for an axe handle, while a resilient, flexible wood like yew could be shaped into a bow that stored immense energy with every pull. The selection process was meticulous, a deep knowledge passed through generations. A craftsperson knew that wood harvested in a specific season and then seasoned slowly in the shade would be less likely to crack or warp, ensuring the longevity of a vital tool. This was not random experimentation, it was a refined, empirical science. They learned to transform the very properties of their materials. A piece of flint, when carefully heated near a fire in a bed of sand, underwent a subtle molecular change. This process, which we call heat treatment, made the stone more predictable and easier to nap into razor-sharp, intricate shapes. The resulting blades were far superior to those made from raw stone, a technological leap achieved not with new resources, but with a deeper understanding of the ones they already possessed. The same sophisticated knowledge applied to organic bindings. A dried sinew from a large animal, when pounded and moistened, could be separated into incredibly strong, fibrous strands. Wrapped tightly around an axe head and a handle, it would shrink as it dried, creating a bond that was both incredibly secure and slightly flexible, able to absorb the repeated shock of impact without shattering. Plant fibers like flax and hemp were twisted into cords that could bear surprising weight, their strength derived from the complex interweaving of countless tiny filaments. This mastery over nature's toolbox reveals a profound truth about these early engineers. They were not limited by their lack of metal or synthetic materials. Instead, they saw the latent potential in every element of their world. They knew which antler would best absorb the blow of a hammer stone, which type of stone could be polished to a mirror-like edge, and which root fibers could be woven into a net that would hold fast against a struggling fish. Their innovations were born from an intimate, lifelong dialogue with the material world, a conversation where every property of wood, bone, and stone was a known language. This deep material intelligence was the invisible foundation upon which every one of their brilliant machines was built. The mind that first envisioned a machine was navigating an entirely new cognitive landscape. This was not a sudden flash of genius, but a gradual awakening of mental capacities we now take for granted. Scholars like Merlin Donald describe a pivotal transition from what he terms an episodic culture, focused on the immediate here and now, to a mimetic one. In a mimetic culture, individuals could rehearse and refine skills through gesture and imitation, sharing complex physical knowledge without a single word. This was the mental soil from which invention grew. To build even the simplest machine required a cascade of cognitive steps. The inventor had to possess foresight, the ability to look at a raw material and see its future form. They needed to visualize an entire process in their mind's eye, understanding with absolute clarity that if I apply force here, the object will move there. This chain of cause and effect had to be planned as a precise sequence where each action set the stage for the next. It was a form of abstract thinking that could look at a river log and no longer see just wood, but perceive its potential as a roller to move a massive stone, or its curved surface as the future hull of a boat. This cognitive leap transformed the world from a set of objects to be used into a collection of components to be assembled. The transmission of these revolutionary ideas relied on a sophisticated, pre-verbal language of demonstration. A master craftsperson would not just tell an apprentice how to shape an axe head. They would show the exact angle of strike, the specific pressure needed, the rhythm of the work. The apprentice learned by watching, imitating, and feeling the correct motion in their own muscles. This shared, embodied knowledge was the glue that held technological progress together across generations. Furthermore, the creation of the most ambitious machines, like a community-wide fish weir or a megalithic tomb, demanded a high degree of social intelligence. It required organizers who could coordinate labor, communicators who could align the group's efforts, and diplomats who could resolve the inevitable conflicts that arose from such immense shared endeavors. The prehistoric mind was not primitive. It was a powerhouse of simulation and problem-solving, constantly running models of the physical world and testing solutions in the theater of thought. Every successful machine was proof of a concept that had already been perfected in the mind long before it was ever built by hand. These new machines quietly rewrote the rules of human connection. The steady pull of the plow did more than just break the soil. It carved the very concept of private property into the land. For the first time, a family's well-being was tied directly to a specific, bounded piece of earth. This was not a field that belonged to everyone. It was a field that could be tended, improved, and most importantly, passed down. The idea of inheritance was born from this connection between machine and earth, creating a lineage of ownership that would shape economies for millennia. Alongside the plow, the rhythmic clatter of the loom wove new social patterns. The intricate, time-consuming process of creating textiles often became a specialized domain, one that frequently fell to women. This was not a relegation to lesser work, but the rise of a vital economic pillar. The demand for vibrant dyes like madder root and rare fibers like flax created the earliest long-distance trade networks, with these materials becoming some of the first true commodities. The weaver, sitting at her loom, was now connected to miners digging for ochre and farmers tending distant fields, her craft binding the community to a wider world. The most ambitious projects, however, demanded a new kind of social contract, moving a megalith for a communal tomb or constructing a vast fish weir was not a casual weekend activity. It required a leader with the vision to conceive the project and the authority to direct the labor. It required planners who could organize the feeding and housing of a large workforce. Most importantly, it required a shared belief among every participant that their back-breaking effort served a purpose greater than themselves, whether it was honoring ancestors or ensuring food security for generations to come. This collective endeavor was the foundation of complex society. The surplus generated by these machines was the fuel for this transformation. When one field, tilled by a plow, could yield enough grain to feed many, it freed hands from the land. This abundance created space for the full-time toolmaker, whose refined axes cleared more land faster. It supported the shaman or priest, who mediated with the spiritual world and preserved communal knowledge. And it inevitably supported the chief or elder, whose role was to manage this new complexity. This was the dawn of social stratification, a move away from small, egalitarian bands. Yet this shift was not merely about hierarchy, it was about a new capacity for collective achievement. The machine, in all its forms, became the quiet architect of civilization, transforming loose networks of families into interconnected communities capable of leaving a mark on the world that would endure long after they were gone. A world without writing did not mean a world without engineering schematics. The complex designs for a toggle harpoon or the precise temperature for firing clay were preserved within a living library of sound and motion. This was the robust system of oral tradition and apprenticeship, a method of knowledge transfer so effective it sustained technological progress for thousands of years. Critical information was not written down in manuals, but woven into the fabric of stories, myths, and sacred songs. A creation myth might not just explain the origins of the world, but encode the best season for harvesting a certain type of wood for bows, or describe the spirit who taught the people to weave, thereby preserving the essential steps of the loom. This embedding of technical data within narrative made the information memorable, repeatable, and protected by its own cultural significance. The rhythm of a song could mirror the rhythmic pounding needed to work a stone, while a hero's tale might detail the correct angle to hold a drill. This was knowledge made sacred, ensuring it was passed from one generation to the next with reverence and precision. Alongside these communal stories was the intensely personal journey of the apprentice. A young learner would spend years beside a master craftsperson, not just being told how to do something, but watching, imitating, and feeling the craft in their own hands. They learn the correct pressure for knapping flint by feeling the master's hands guide their own. They understood the right sound of wood being properly worked, or the exact smell of clay at the perfect stage for firing. This was knowledge transmitted through the body itself, a deep, tactile understanding that could never be fully captured by words alone. Ritual and ceremony played a crucial role in this process, acting as scheduled repetitions of vital information. A community's seasonal gathering might include a reenactment of the first hunt, complete with a demonstration of how to assemble and throw a spear. These events were not mere entertainment. They were mandatory refresher courses that reinforced the technical standards upon which survival depended. This interlocking system of story, mentorship, and ritual created a resilient web of knowledge. It was how the precise method for heat-treating stone to make it easier to flake could remain unchanged for centuries. The fragility of this system, however, became apparent during times of great upheaval. If a community was dispersed by conflict or a generation of masters was lost to illness, the intricate chain of demonstration and song could be broken forever. The knowledge of how to build a specific machine, perfected over 1,000 years, could vanish in a single generation, leaving behind only silent stones and unanswerable questions for us to find. A corroded lump of bronze and wood, resting for 2,000 years on the floor of the Aegean Sea, silently refutes our entire timeline of mechanical history. When sponge divers first pulled the Antikythera mechanism from that Roman shipwreck over a century ago, they had no idea they were holding the world's first known analog computer. This wasn't a simple tool, it was a labyrinth of at least 30 precise bronze gears, all mounted within a wooden case and turned by a hand crank. Its dials and pointers could predict the movement of the sun and moon, chart the phases of the lunar cycle, and even forecast eclipses years in advance. It was a miniature mechanical universe, a device of staggering complexity that seems to have arrived from nowhere. So where did it come from? The genius of its design lies in its application of principles we thought were modern. It used a differential gear, a component once believed to have been invented in the 16th century, to calculate the moon's variable speed across the sky. This means that over 2 millennia ago, an unknown engineer understood how to use interlocking bronze wheels to model the subtle dance of celestial bodies with breathtaking accuracy. This device was a physical manifestation of astronomical knowledge, a machine that turned abstract mathematical theory into a tangible, turning prediction. The Antikythera mechanism forces a difficult question. Was it a miraculous anomaly, a lone spark of genius in the classical world that was snuffed out by history? Or does its existence point to something far more profound? Perhaps it was not the beginning of mechanical science, but its peak. It could be the sole surviving relic of a long and sophisticated tradition of precision engineering that has otherwise completely vanished from the record. Think of the knowledge required to build it. The creator needed a deep understanding of astronomy to know what to calculate. They needed advanced metallurgy to cast and cut such fine, intricate gears. And they needed a revolutionary concept of how a machine could simulate the laws of nature. This was not a technology that sprang forth fully formed. It hints at generations of prior experimentation, at workshops filled with prototypes and failures that have been lost to time, decay, or the melting pot. The ship carrying it was a Roman vessel, likely transporting loot from the Greek world. This suggests the mechanism was not unique, but perhaps one of many such devices, a prized possession of a scholar or a temple. Its very presence on that ship implies a world where such machines were known, valued, and traded. If one could be built, why not others? What other mechanical marvels, perhaps used for navigation, timekeeping, or even early forms of calculation, might have existed in the libraries and workshops of antiquity? The silent gears of the Antikythera mechanism do not just predict eclipses, they predict a gaping hole in our understanding. They suggest that the journey of the machine, from the first lever to a device that could model the cosmos, may have been far more advanced and far more tragic in its loss than we ever dared to believe. The silent gears of the Antikythera mechanism present a mystery so profound it seems to defy explanation. It is a human tendency to fill such voids in our understanding with the extraordinary. When faced with the scale of the megaliths or the precision of a forgotten machine, a tempting narrative emerges, one that credits these wonders to visitors from other worlds or to a super-civilization lost beneath the waves. These stories are compelling, but they are built on a foundation that crumbles under the weight of actual evidence. The principle of Occam's razor suggests that the simplest explanation, the one requiring the fewest assumptions, is most often the correct one. And the simplest explanation is not a spaceship or a sunken continent, but the enduring power of the human mind working in concert across generations. To attribute the toggle harpoon or the potter's wheel to extraterrestrial intervention is to commit a profound disservice to our ancestors. It strips them of their rightful legacy as innovators, reducing their patient, hard-won genius to a mere receipt of alien technology. The archaeological record tells a very different and far more compelling story. It is not a story of sudden, miraculous gifts, but of slow, cumulative progress. We can trace the axe from a crudely chipped hand tool to a beautifully polished nephrite masterpiece over thousands of years. We can see the fish weir evolve from a simple line of stones to a vast, engineered labyrinth. Each generation stood on the shoulders of the one before, making small refinements, learning from failures, and passing that knowledge along through song and demonstration. This was a global phenomenon, not the secret project of a single advanced culture. The bow drill appeared independently in the Arctic and the deserts of North America. The principle of the lever was discovered and rediscovered wherever humans faced a heavy load. This pattern of parallel invention proves that when faced with similar problems, human ingenuity, fueled by curiosity and necessity, will find strikingly similar solutions. The real story is not one of a forgotten golden age, but of a slow, steady dawn. It is the story of countless unnamed individuals, each adding their own small insight to a growing body of knowledge. Their collective patience, their willingness to experiment, and their profound connection to their materials are what truly built the first machines. By letting go of the fantastical, we can finally see the genuine marvel right in front of us, the incredible capacity of ordinary people to achieve the extraordinary through time, trial, and collaboration. That grooved stone resting in a museum display case holds a silent story, waiting for the right methods to give it a voice. How can we be certain it was a shaft straightener and not just a rock worn down by natural processes? The answer lies in the rigorous science of modern archaeology, a field that has moved far beyond simple guesswork to become a disciplined form of detective work. At the heart of this process is experimental archaeology, where researchers become inventors themselves. They gather the same materials, use the same techniques, and attempt to recreate the exact tool or machine. A team might spend weeks carving a wooden spear shaft and then patiently drawing it back and forth through a replica grooved stone that has been heated by a fire. They document the resulting wear patterns on both the shaft and the stone itself. Does the groove develop a specific polish? Are there microscopic striations that match the direction of the wood grain? This hands-on testing transforms a static object into a dynamic piece of evidence. This leads to the second critical method, use wear analysis. Under high-powered microscopes, archaeologists examine the edges and surfaces of artifacts for tiny clues invisible to the naked eye. The polished sheen left by repeatedly working wood is distinct from the scuffing caused by scraping hides or the crushing damage from breaking bone. These microscopic signatures are like a unique fingerprint for each task, allowing scientists to say with confidence whether a stone tool was used for carving, butchering, or, in the case of our grooved stone, straightening wooden shafts. The context of the discovery is equally vital. An object's story is told by its companions. Was the grooved stone found near a hearth, alongside unfinished spear points and grinding slabs? This specific setting paints a vivid picture of a tool maintenance area, strengthening the interpretation that it was part of a workshop dedicated to perfecting hunting equipment. Finally, ethnographic analogy provides a living bridge to the past. By studying how contemporary hunter-gatherer and traditional societies use their tools, researchers can draw powerful parallels. Observing an artisan in a community today using an almost identical grooved stone to straighten arrows offers a compelling, real-world model for how the ancient artifact functioned. This is not about assuming all cultures are the same, but about understanding the universal physical principles that lead to similar solutions. When the evidence from experimentation, microscopic analysis, contextual clues, and cultural analogy all point in the same direction, we can reconstruct the purpose of these ancient objects with remarkable certainty. These methods allow us to do more than just label an artifact. They let us witness the hands of the craftsperson at work, turning a silent stone back into a vital machine. Technological progress is a story we often tell backwards, assuming every step forward is permanent. But the path of invention is littered with dead ends and abandoned machines. Entire technologies that once defined a way of life could vanish in a generation, not from a lack of genius, but from the fragile nature of the societies that nurtured them. The collapse of a complex civilization like the interconnected Bronze Age empires serves as a stark example. These were societies that supported specialist metalworkers, engineers, and scribes. When that intricate network of trade and governance shattered, The specialized knowledge held by those individuals had nowhere to go. The workshops fell silent, the apprenticeship chains were broken, and the formulas for creating high-quality bronze or the techniques for building sophisticated water systems were simply forgotten, waiting to be rediscovered centuries later. Migration could also render a brilliant machine obsolete overnight. A community that mastered the fishing weir for a specific river delta would find that knowledge useless upon moving to an arid mountain range. The machine was perfect for its context, but the context disappeared. Similarly, the entire technological system could collapse if a single critical resource vanished. Imagine a culture whose entire toolmaking relied on a single quarry of unique, fine-grained stone. If that quarry was exhausted, or if a shift in climate or territorial disputes made it inaccessible, the knowledge of how to work that stone became a memory without a medium. There was no point in teaching the next generation how to nap a material they could never possess. Sometimes loss came not from catastrophe, but from a quiet, practical choice. A simpler, good-enough technology could replace a more complex one if it was easier to produce, maintain, and repair with readily available materials. Why invest weeks in crafting a complex device when a simpler tool made from a branch and a sharp rock gets the job done almost as well? This principle of least effort is a powerful force in human history, often favoring resilience and accessibility over peak efficiency. Finally, knowledge itself could be a vault sealed by tradition. If the craft of building a sacred object or a powerful machine was considered secret, taught only to a select few initiates, it lived on a razor's edge. The unexpected loss of a single master without a successor could be enough to lock away that invention forever. This great forgetting is a humbling lesson. It reminds us that our technological world is not an inevitable ascent, but a delicate tapestry, one that can be rewoven, but also unraveled by the currents of time. Our journey from the first lever to the edge of complex gearwork reveals a legacy of profound ingenuity. These forgotten inventions were not crude attempts but sophisticated applications of physics, born from relentless observation and a deep dialogue with the natural world. They were the quiet, patient work of countless individuals whose names are lost to time, yet whose innovations fed communities, clothed populations, and raised monuments that still stand today. This drive to build, to solve problems with a concept made real, is not a recent development. It is a fundamental thread in the very fabric of the human story, a testament to our shared capacity for wonder and creation. The science fiction author Isaac Asimov once reflected that the most exciting phrase in science, the one that heralds new discoveries, is not eureka, but that is funny. It is in those moments of curiosity, when an observation does not quite fit the expected pattern, that the deepest truths are often uncovered. So we are left to wonder what other funny artifacts lie waiting in the soil or resting in museum drawers, holding the silent secrets of our ingenious past. Their stories are not yet over. We would love to hear which of these first machines most captured your imagination. Was it the elegant toggle harpoon, the transformative plow, or the mysterious Antikythera mechanism? Share your thoughts in the comments below and subscribe for more journeys into the mysteries of history.